Hello everybody. I'm recording this one as well because what the heck, right? So hopefully this helps if you're watching it. If nobody watches it, well, I guess it's just me talking to myself, okay? So we're going to be talking about exponential function graphs, all right? Hopefully some of this you might recall from Algebra 1, all right? And so exponential functions can be classified either as growth or decay, depending on whether they go up or they go down, right? So, that being said, all right, let's do a couple things first. I'm going to set up a couple XY charts next to these graphs here. Okay? So an asymptote. What is an asymptote? All right? The asymptote is a curve which approaches, a line which approaches a curve but never actually meets. Okay? So what does that mean? All right? So what I want you to do is, what I'm going to do is I'm going to plug each of these into my calculator, right? So 2 raised to the x power. Okay? And what I'm concerned about is the table of values, right? So at -1 we're at 0.5, 0 we're at 1, 1 we're at 2, 2 we're at 4, 3 we're at 8, and that's where I'm going to stop. Okay, so I'm going to graph those points right here. Okay, so at -1, 0.5, 0 we're at 1, 2, 4, 8, so on and so forth. Okay? So, as you can see, this is growth, right? It's going up. Okay? We graphed it, basically using our table of values, but we want to talk about the asymptote. So if you scroll back, if you keep going back towards the negative side, you will see that this number keeps getting smaller and smaller, okay? But it will never actually reach 0. And part of the reason behind that is this, right? So 2 to the 0 power is just 1, right? 2 to the -1 is just 1 over 2. 2 to the -2 is just 1 over 4. 2 to the -3 is just 1 over 8, okay? So on and so forth, right? So what happens is it's going to continue to get smaller and smaller, right? But it'll never actually reach 0. So therefore our asymptote, okay, is going to be y is equal to 0. Asymptote. Okay? All right? And if you notice, okay, and when we get to transformations, you'll see that, all right? There's nothing after any of these, right? We don't see anything attached to these numbers, right? If you look down below, one of our problems here, one of our homeworks, you see that we had this +1 attached here, right? And so what did that mean? I mean, our graph was shifted up 1, right? So in all of these, technically, all right, this asymptote is listed there, we just don't see it. It's +0. Okay, so in all of these we have a +0 here, right? You can add 0 to something, it doesn't affect anything. Okay, but what that signifies and what it lets us know is because we don't have anything back there, our asymptote for all 4 of these is going to actually be y equals 0. Okay, so you'll see that for all of these, right, you'll notice that anytime we're related to this x power, right, none of them are going to actually ever meet or reach 0, right? Because as you can see from the example above, right, 2 to the 0 power is actually 1. So in all of these, our y-intercept is also going, whoops, it's actually going to be 0, 1. Okay? So let's graph the rest of these using our calculator. Whoops. So you'll notice in this one, okay, when you plug this into your calculator, oh crap, -3, -2, -1, 0, 1, 2. Now at 0, for all of these, it's going to be 1. Okay, now you'll notice this time, right, when we get negative 1 back here, this is actually going to be equal to 2. And this will be actually equal to 4. And this will be actually equal to 8. And as x approaches positive infinity, right, this becomes a 0.5, 0.25, so on and so forth. Right? So when we go to graph this, you would see that negative 3, 8, 4, 2, 1, and smaller and smaller. Okay? All right, and so this would be classified as decay. And again, our asymptote, that line will never cross, is again y is equal to 0, because we'll keep getting smaller and smaller here, okay, but it'll never actually go below 0. Okay? And then it's asking for the average rate of change. So it wants to know what is the average rate of change when x is equal to negative 1, which in this case is 0.5, to when x is equal to 3, which in this case is an 8. And so I want to know what is the average rate of change between those 2 points. So first you're going to say that it's going to be something positive, right? Because we are going up between those 2 points. So x1, y1, x2, y2. So we're going to go 8 minus 0.5 all over 3 minus a negative 1, which will be 7.5 over 4, which is 1.875, or 15 over 18, or 8, sorry. Okay? All right, and then the average rate of change here, right, between negative 4 and 0, looks like we're going down. So at negative 4, where are we at negative 4? I think we're at 16, right? Yep, okay, so at negative 4, we're at 16 on this graph, and then at 0, we're at 1. So again, we anticipate this one to be going down between those. So let me shrink this down here, whoops. There we go. x1, y1, x2, y2. And so 1 minus 16 over 0 minus a negative 4, which will give me negative 16 over a positive 4, which is a negative 4 over 1. Okay? All right, for these last two, okay, let's see something a little different, right? So when we plug this 2 raised to the negative x, and check out our table, what you'll see is something very similar to the x and y table in number 2. Right? At negative 3, we're at 8. At negative 2, we're at 4. Negative 1, we're at 2. 0, 1, 1.5, 2, 0.25, so on and so forth. Okay? So what's happening here is as we approach positive infinity, our graph is going down. We have a decay problem here. So negative 3, 2, right? Here's our curve. Again, this is a decay, and our asymptote is y is equal to 0. Okay? And then for this guy here, even though it's a fraction being raised to a negative power, you'll find that this one is opposite of the guy to our left here. And you will find that at 0, again, we're still at 1, but at negative 1, we're at 0.5, negative 2, 0.25, at 1, we're at 2, 2, we're at 4, 3, we are at 8. All right? So, what we can say here is that we have a growth problem okay, with our asymptote at y is equal to 0. Again, it will never go below that line. Okay? And so to summarize, right, fractions being raised to a power greater than 1 creates exponential decay, like number 2. Numbers being raised to a negative, or numbers greater than 1, so like number 3, being raised to a negative power creates decay. And like number 4, fractions being raised to a negative power creates exponential growth. Okay? So, from Algebra 1, all right, these are not given on your Regents, okay, but hopefully you guys recognize these two formulas, okay? Growth looks like this, where A is our initial amount, R is our rate, and T is the time, right, the time span we're in reference to. Okay, so growth has got a plus there, and decay's got a minus. So I think that's kind of easy to recall, right? When you're growing, you're adding, you're decaying, you're subtracting, right? So, and then the first problem here, the population of Winnemucca, Nevada, can be modeled by this equation right here, where T is the number of years since 1990. So it wants to know what is the initial amount? What is our A value here, right? And so our initial amount, what we're starting with, was our population in 1990 was 6,191 people. Okay, and then by what percent did the population increase? Okay, so to get a better picture of that, I'm going to rewrite this guy like this. Okay, and so here, when I write it like this, you can see that our rate, or our R, is 0.04. Or, we're talking percentages, 4%. Okay? And so when it's some sort of growth problem, whatever is being added to that 1, right, that is your rate here. Okay? All right. And the next one. Okay, the amount Y in grams of a sample iodine 131 after T days is given by this equation right here. Okay? And so the question is this growth or decay? Right? Now, if you read down the problem, in letter B, it says what percent of the substance decays each day, right? So sometimes it helps to maybe read forward, but as you can see here, right, we have a fraction inside the parenthesis, right? A fraction being raised to a whole number will create some sort of decay, right? So identify the initial amount of the substance. Well, that's our A value, right? And what comes before the parentheses is that 50. Then it's asking how much it's decaying each day. Right, so we can't just do what we did up in the last one, but if we write this out, right, it's 50 is equal to 1 minus R is equal to T. Okay, so in this case, right, how do we get 1 minus R is equal to 0.92? All right, well, when you solve this out, you would find that R is equal to 0.08. Okay, so that means our equation here is 50, or 1 minus 0.08 equal to T, and 1 minus 0.08 will give me that 0.92 inside the parentheses. So what percent of the substance decays each day? 0.08, or 8%. Okay, so what that means is, what does the 92 represent? Well, this is how much substance is left after each day, right? So think of it like this. If you, all tests are, tests and quizzes are usually out of 100, right? So let's say you get a 90, let's say you miss 8 problems, right? Let's say you missed 8. So what that means is you got 92% of that test left, right? That's what you got correct. And so think of it like this, right? After that first day, right, well, we have 92% of our original product, right? We have only lost 8 points, or 8%. And then, after the second day, well, we got 92% of what we had that first day, right? So you keep taking 92% of what you have left each day. So that just represents the amount of substance left after each day. Okay? Number 1, number 2 deal with some sort of, they're a little more chemistry-like, right? So an isotope of cesium-137 has a half-life of 30 years. So if 1 gram of cesium-137 disintegrates over a period of 90 years, how many grams of cesium-137 would remain. Okay, so let's first talk about how fast these things are decaying. Right, so when we're talking about half-life, okay, what that means is you have half of your substance left after each cycle. Okay, and so in this case, we're left with 1 gram of cesium. So after one cycle, right, we'll be left with half of what we started with, which in this case would be half a gram, right? And so we want to find out how much is left after 3 cycles. And so this cycle is represented by however many years, right? And so our cycle is represented by 30 years. So after 30 years, we're losing half of this cesium-137. Okay, so our rate, or what we're decreasing by, is 0.5, right? We're losing half of our amount each time, or what do we have left? 0.5, right? So our equation is going to be y is equal to our initial amount, 1, times 1 minus 0.5 raised to the t, and we'll talk about t in just a second. So here's y is equal to 1 times 0.5 raised to the t, right? So what is our t, right? How many cycles do we have? Well, if 30 years represents 1 cycle, and we're going over a 90-year span, that means we went through 3 cycles. Okay? So, y is equal to, I'll just leave that 1 out, 0.5 raised to the 3. And what do we get? 0.125, which makes sense. We could find that one easily. Like, you have 1 cycle, we're starting with 1. After 1 cycle, you're losing half, so 0.5. Cycle 2, we're losing half of that, so 0.25. And then cycle 3, 0.125. Okay? All right, so the last one. This guy is transporting sodium across the hall, I guess, or across the building, right? Sodium-25 was to be used in an experiment, but it took 3 minutes to get the sodium from the reactor, or get the sodium from the reactor to the laboratory. Okay, so what's happening here is this person, this experimenter, right, is walking sodium-25 from one place in the building to the other, right? So he's starting with 5 milligrams of sodium-25, right? And it's going to take him 3 minutes to walk from the reactor to the laboratory. And so he wants to know how much of that sodium-25 is going to be left, right, after walking 3 minutes, and our half-life of this sodium, or we're losing half of our substance every 30 seconds. Okay, so again, another half-life problem. Right, so y is equal to, our initial amount is 5. We're losing half of our sodium, right, after each cycle. Right, so 0.5 is what we have left, right, is what is remaining. And so we want to know how many cycles that is, right? So 3 minutes is equal to how many seconds? Well, that's 180. So we're going to go 180 divided by 30 will give me 6 cycles. So how many cycles it's going to go through? 6. And so 5 times 0.5 raised to the 6th power, we're going to have 0.078125 milligrams left of this sodium when we get to the laboratory, which isn't a whole lot. So maybe he should have grabbed a little more. Okay? But anyway, here is Unit 4, Day 11. Okay, so hopefully this helps you guys. All right? Utilize these videos if you want. There's an answer key I sent to everybody as well. Okay, so make sure to take a look at that, and good luck.